Welcome to another MathCast. In this episode, we're going to be taking a look at the surface area formula, looking at a solid of revolution and being able to find the surface area of the solid. This involves both the arc length formula as well as a little bit of things that we learned in geometry. In class, we talked about the surface area of a cone, and at the time, I just told you what the surface area of a cone was. We recall from geometry that it's pi r L, where L is what we call the slant height. I have a cone here for this particular problem, a 3D rendering. Let me go ahead and just sort of label it a little bit for us. This edge is called the slant height of the cone. And the radius of the cone that I want to consider, so if we think about the radius here, right, it's going to work its way around through the back side. We've got the radius of the cone is defined to be r. So we're going to let our radius be r. And then we also have the height of the cone, which is this vertical distance from the apex down to the center of the base. And we'll let that be the height. Well, in considering this particular cone, we were told in geometry that the formula is pi r L, and what I want to do in this video is actually go ahead and use our surface area integral to prove that result. Now, in order to do this, it's probably a good idea to focus on this triangle that I've created here. So let me go ahead and set up sort of a better representation of that. If we have the vertical axis here, horizontal axis, get those in place. And I want to look at basically the slant height being revolved around the y-axis. So my figure is going to look something like this. So I'm going to revolve it around the y-axis, and my points here, this is the radius r, this is the height h, and this is the slant height, but we notice the slant height is nothing more than r squared plus h squared because of the fact that this is a right circular cone and therefore that is a right triangle. We're going to use that to our advantage here in a second. So if I'm looking at actually doing the rotation of the cone for these particular values, I need to know what the equation of the line is I've drawn here. So this is the point r0, and this is the point 0h, which if we recall from our algebra studies, how to find the equation of a line through 2 points. This is the line y equals minus h over r times x plus our y-intercept is h. And so this is the formula that we're going to be using to do our analysis. So recall from class that if I want to find the surface area of a solid of revolution, this is equal to the integral of 2 pi r L, and this is where r is the radius of the cone, and L is the slant height, or the arc length is how we're going to think of it, of the piece. So for this particular example, we would be integrating, if I'm looking here for the axis of revolution, we're integrating from 0 to r of 2 pi, and then if I think about my radius, well, the radius of each of these rotations is nothing more than this distance, which changes based on whatever your x value is. So the radius here, which is this length, is nothing more than an x value. And the x values, of course, range from 0 to r. It can be anything from 0 to r, that's the radius length. And then the arc length here is the square root of 1 plus, well, typically we say dy dx squared dx. So this is the arc length element ds. And so another way to really think about this formula, and this is the way I would like for most of you to think about it, is 2 pi r ds. We are integrating sort of with respect to the arc length, and depending on what's the most convenient form of the arc length formula to take, that's the way that you should set up the problem. In this case, it's convenient for us to integrate with respect to x, and so I've set up the arc length element so that it reflects that. Well, if I fill in the rest of the formula, this is the integral from 0 to r 2 pi x 1 plus dy dx is nothing more than the slope of this line, which is minus h over r squared. Do a little bit more work on this. This is the same thing as 2 pi x square root of 1 plus h squared over r squared, which finally gives, if I get a common denominator here, 2 pi x over r square root of h squared plus r squared, and look at what happened. This r squared plus h squared term showed up, so this is the integral from 0 to r of 2 pi over r times L times x dx. And if you do the integration here, so let's create a little space here and finish this problem out. If you do the integration here, it's the integral from 0 to r of just x dx, where I've got all this additional stuff out in front, the 2 pi r over L. So we wind up with x squared over 2 evaluated from 0 to r, or r squared over 2 because the 0 doesn't contribute. What you notice then is that the r's cancel, leaving just one r in the top. So we have 2 pi r L over 2, or pi RL, as we claimed at the beginning. So that was actually a very important thing that we just assumed at the beginning of our work involving surface area integrals, but we've since come back now and shown that it's true using the formula that we derived. It's actually a pretty neat application of surface area. The problem with the surface area integral is, as you can see, I've got a function of x here, and then I have a square root involving either x or y or something like that. Makes those incredibly difficult integrals to solve by hand. And so a lot of these problems I'm going to be asking you to set up the integral but not actually solve it. There's a couple on your homework that you're going to be looking at where I ask you to go ahead and solve it, but those are pretty easy engineered examples so that the work comes out okay so you can actually do the integral. On the exam though, it's more likely you're just going to be setting up integrals of this type. All right, thank you for watching.